Okay, so we've gotten into probability, right? What I want to do is really quickly, I want to give a quick summary of this chapter, and I want to show you, because sometimes it helps for, instead of everything just kind of standing alone, if I kind of organize what we've learned so far and how it all falls in the whole probability scheme of things, it kind of helps people just have a deeper understanding of what we're talking about. So today we're going to talk about something called independent and dependent events. But before we get to that, here's what I want to show you. I'm going to kind of write this kind of small, but to give you an idea, if probability was a heading, right? And we're talking about how everything we're learning falls under that heading of probability, that concept. Here's what I would say. I'd say, okay, probability, there's two major types of probability. And you'll notice all these because we've talked about all of them so far. There is theoretical. Remember, that's where you use math to give a good educated guess at what the chances are something happens. And then there's experimental. And that is, of course, where you're dealing with, you're dealing with actually playing a game or actually doing something and see what the outcome actually is. And then sometimes, of course, you can use that to predict future outcomes. But theoretical, remember I told you the other day, most of our lessons will fall under the theoretical because that's where the main part of the math is. So what we've also learned is up to this point, we've learned, remember we started with theoretical, we started with simple events. And that was like a simple game. Like one little thing like rolling dice. What's the chances of, rolling something that's not a 2 or something like that, okay? Under theoretical, though, we also, last time you guys were with me, we also talked about a harder game. Now, it is kind of related to simple events, so I'll put like this little arrow here, but it, remember, was on compound events. And remember, compound events, probability of compound events was basically having like more than one event happening to play this game. It's basically a harder game. Now, what I want to share with you, and the whole reason why I'm sharing this with you is because we are focusing under compound events. We're going to continue with compound events. But actually there are, and for the sake of 7th grade, learning what we're going to learn in 7th grade, we'll say there are two types of compound events. There are something called independent events, and there are something called dependent events. And that's, of course, what we're talking about. Now, a lot of what we talked about the other day when it came to compound events, we were mainly dealing with what were called independent events. So we're going to see a little review on that today. But then you'll see that sometimes the game on compound events, sometimes it changes. Okay? And there's things that are called dependent. So that's what our focus is today. All right? So I'm going to pause before we get, bless you, to our vocab. And I want to share with you guys something. All right? So let's say, this is my little corny little makeshift game I've got for you guys. Ta-da! Okay, those are cards. I felt that I didn't put them face down because it'd be white on white and you wouldn't see them. So I kind of made a little outline and a little box to cover the number for the most part. But there's our 4 cards. All right? And the goal in this game, this compound event, is we want to know what is the probability of choosing a 1 and then turning around and choosing a 4. This is just like the other day, okay, when we talked about compound events, okay? So you'll see, what's the probability of choosing a 1 and then a 4? So we'll eventually get to the major part and find the final answer of probability. But what I want to do is just kind of play the game a little bit with you guys. So if I take a look here, if I go to play the game, remember this is compound events. I need to do this, and then I need to do that. All right? So if I turn around, and I'm just going to, I can shuffle them up, whatever else. And I go ahead and say, okay, well, shuffled up. I'm going to choose at random. I'm going to try to choose a 1. So I turn around and say, okay, maybe, I got a 1. All right? So far I'm about maybe have a good chance of winning the game. Okay? Now, by the way, when I went to choose that 1, what was my probability of choosing the 1? By the way, if you don't already know, I guess I should have clarified this. Under here is just 1, 2, 3, 4. It's very simple. So if that's the case, what was our probability of choosing a 1, guys? 25%, but yeah, 1 out of 4, right? 4 total cards, 1 was on one of the cards, so 1, I have a 1/4 chance, okay? Now, I flip it back over, and now I'm going to try to choose a 4, okay? What's our probability of choosing a 4?
104.
Yeah, it's the same. It's not a trick question. There 4's on one of the cards is a total of 4 cards. 1 out of 4. So, I don't know. Who wants to give me which card should I pick?
The bottom left.
Bottom left. Here we go. Oh! All right, Ashley won. So, all right. So, all right. Now that is, of course, playing a silly, simple compound event game like we were talking about the other day. Okay, and we're not doing a tree diagram or anything right now, but that's what that is. Okay. Okay. Now, here's what I want to do. Same game, same cards. But there's going to be one little difference, and we'll talk about that in a bit. Okay. Kind of shuffling them around. All right, here we go. We're gonna same game, right? Like we have to choose a 1 and then choose a 4, same cards. I'm going to go ahead and with these cards, I'm going to go ahead and choose 1 to try to get 1. Hey! Chose a 1. All right. So I turn around, shuffle them up. Okay, same cards, right? By the way, what was our chance of choosing a 1?
25%.
Okay, it was 1 out of 4 or 25%. Okay, 25%, but it was mainly 1 out of 4. Okay, I want to focus on the fraction. Now, here's the thing. I have my 1. I'm going to play the game, but here's the difference. Once I choose the 1, I don't put it back. Still trying to choose the 4. Let me ask you guys, what is our chance of choosing a 4?
1 of 3.
1 of 3.
Or 3.
All right, who wants a shot? Middle, let's try it out. Oh! All right, so you had a 1 in 3 chance, all right? Unlucky. So, all right, so, ladies and gentlemen, what you guys just experienced was the difference between an independent and a dependent event. All right, the games, take a look. The games, of course, are very similar, but this one, like we just did, that is called a dependent event. This, of course, like we are used to in our past lessons, was an independent event. Now let me ask you guys. First of all, just a quick description. What was the difference in the game rules?
The second time you played it independently, or no, the second time you did it,
Yep.
You took away the 1 you.
So, during the game, right? The dependent, after I chose my first card, I took it away. I didn't put it back in the game. Okay? That is a dependent. The independent, it just went right back and we started new. Okay? Now let me ask you, talking about looking at our basic probabilities, how did that dependent change from when we were comparing it to the independent? How did it change our probability part? Our chances of winning? No one can see the difference between that and that?
It lowered your chances. I mean, it increased your chances.
It lowered the bottom number, but what that means is it increased our chances. It made our chances better. Okay, we had a 1 in 3 chance, 1 only out of 3 rather than a 1 out of 4. That's an increase of chances. It's a better chance. It's more likely, right? We've talked about using words. It's more likely to happen than that is. Okay? So what I want to do is, and we'll come back, we'll kind of flip back and forth here, but I wanted to just show you an example of a game and a difference of independent versus dependent events. We're going to get more into it, though, when it comes to our vocab here. So here we go. Our very first word is independent events. Everyone?
Independent event.
So here's what the book says independent events are. It says these are 2 or more, because it could be more, 2 or more events in which the outcome, sorry, I should move it over. 2 or more events in which the outcome of one event does not affect the outcome of the other event. Two or more events in which the outcome of one event does not affect the outcome of the other event. So those of you guys that are good in AB class, right, and are good readers and you have good vocab skills, not talking about probability, I'm just talking about the English language. What does independent mean? I heard one word, like a loan.
Yeah, like
Separated. Okay.
You don't really need anybody else to take care of for you.
So separated from maybe a caretaker that would take care of you. You don't need that caretaker. Okay.
Not independent.
Not what?
Independent.
You mean not
Not dependent.
not dependent, right? Using the prefix in, right? Not dependent. So that is another way to think about it.
Doing it on your own.
Yeah, doing it on your own, right? So we're going to come back to this, but you guys are absolutely right. That's what independent means. Okay? So it's better to talk about the next word, and then we'll come back to how the independent events, affect each other or don't affect each other in relation to our next word. So here we go. By the way, in your little box there, I just have a little example, and it pretty much is kind of like the game we just played in some ways. All right? This is an example of an independent game or an independent compound event. So choosing 2 letters from a hat, but after you choose the first one, you put it back. So you put the first letter back. Choosing 2 letters from a hat and putting the first letter back. Of course, after it's chosen. Bless you.
That's you.
Okay. Our next word, you guys probably know where this is going. Dependent events. Everyone?
Dependent events.
So here's what dependent events are. These are 2 more events in which the outcome of one event affects the outcome of the other event. The outcome of one event affects the outcome of the other event. So in your little box off to the side, you can write down choosing 2 letters from a hat and not putting the first letter back. We saw how that affected the probability of that second in our game, right? It went from choosing that 4 became 1/4 to a 1/3. It increased our chances of winning the game. At least if you chose the 1 the first time around. Bless you. All right, so let me ask you this. We just talked about independent events or independent. What does dependent mean? What does dependent mean?
It means when like you need someone to take care of you.
So it's the opposite of what we just talked about, right? It's actually like you need someone to take care of you. Anyone else have something to...
Not independent.
It's not independent, all right? So it's like a double negative, right? Not independent, so it's an antonym, right? Okay. So independent means you don't need, and we're focusing on people, right? You don't need someone to take care of you. Dependent means you need someone to take care of you, okay? But what you can think of is that dependent is, here's how I always like to explain it, is the second event, or in this case, the probability of the second event depends on the outcome of the first event. Bless you. All right. So in this case, when this outcome changed, it was because the fact that after we chose that 1, we didn't put it back. It was dependent on the first number or the first event. Okay? So when we didn't put it back, it changed the probability. All right? So the probability all depends on the second event, all depends on the first. When this one, they were completely 2 separate games. Let's play that game, and then let's play that game. It just happened to be that they're all part of one game, but I mean, they were 2 independent. They could stand by themselves. They didn't need the help of the other to affect the probability. Okay, they were independent. All right. Now, what I want to do for one more second here is I want to go back to using a tree diagram just really quickly, and trust me, I'm going right into this is going into our lesson here. Okay, we didn't talk about this when it came to probability of compound events, but I want to talk about it now. All right. So let's build it. I'm going to build a tree diagram. Here we go. During this game, our first pick, what were our choices? What were our possible outcomes, guys? What was our sample space?
1, 4.
1
4.
and 4, that's it? 1, 2, 3, 4. So 1, 2, 3, 4. Now, afterwards, right? After I chose it, put the 1 back, what was our second event? What was our sample space? 1, 2, 3, 4. It's the 4 branches, right, coming off. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Guys, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many total outcomes are there? 16 possible outcomes. Right? 16 possible outcomes. Now let's talk about this. 16 possible outcomes. I want to talk about the probability. Now we're going to find the probability. The winner is choosing a 1 and then a 4 in that order. How many different ways can we choose a 1 and then a 4? I don't know about you guys. I only see it in one exact spot. A 1 and then a 4. We have a 1 in 16 chance to win this game. That's not very good odds, right? Okay? Now, I really actually don't care about the odds. Here's what I care about. I'm going to take this probability up here. I'm going to put that right here. There's our answer. Let me ask you guys something. Probability of the first event, probability of the second event, the probability of that actually happening. Can anybody notice anything that may be an algorithm? Those of you that don't want to build tree diagrams. Say that one more time.
The denominators, like 1/4, 1/4, and 16. 4 times 4 is 16.
4 times 4 is 16. Okay. Anyone want to add on to that? Ladies and gentlemen, state testing is coming, and this is something you learned in elementary school. So it's not probably a good idea to not be able to see it. Okay. You multiply the numerator and the denominator. Is it safe to say, ladies and gentlemen, that that is multiplication of fractions? Wouldn't that describe how you multiply fractions, everyone?
Yes.
Yeah. So, Jack, we go 1 times 1 is 1. 4 times 4 is 16. I tell you what, if you don't understand this and you don't want to do this, feel free to build a tree diagram every single time. I'm leaving that up to you guys. I'm trying to show you an algorithm here, a quick way of finding out the probability of compound events, because you're going to need that today to be able to do today's homework. If you take the probability of each simple event and multiply those probabilities together, you actually get the probability of the compound event happening. Okay, so that is what you're going to see today. All right, so here we go. Let's go ahead. Let's grab our worksheet. All right, let's take a look at problem number 4. All right, so this says, and directions now are huge, because now we have even more going on with our probability, and we need to know how the game is played, because we now know that probability is affected. Is it a simple event? Is it a compound event? If it is a compound event, are they independent? Are they dependent? That all matters. Okay, so I'm going to read this. It says the 2 spinners at the right are spun. Find each probability. Okay, so I'm going to go ahead and look here, because I'm spinning the first one first. Number 4 says, what is the probability of spinning an odd number? So, ladies and gentlemen, the first step is find the probability of the first event. So if I take a look here, let's see. There's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. We're just dealing with a simple event right now. And odd numbers are, there's 1, 2, 3, 4 of them. We have a 4 in 8 chance, or a 1 in 2 chance of spinning an odd number. Now, step 2. I'm going to put a little star by step 2. By the way, next to step 1, we're going to put this little reminder. Reduce, because remember, we need to simplify or reduce those ratios if possible. So here's why we put a star by step 2. Because when we're finding the probability of the second event happening, we need to be extra careful. Okay? We need to know, did something change? Is this one dependent on what happened the first time around? And here's the thing. On this particular one, we have a second spinner. Okay? It's not, the first spinner doesn't even matter. First event doesn't even matter. I mean, it does when it comes to probability, but it did not change the second spinner. It's not like we spun something here and then all of a sudden half of these choices vanished. Okay? Nothing happened to the second spinner. On the second spinner, we want to know, what's the probability of choosing an A? Well, 1, 2, 3, 4, 5, 6 sections on this spinner. How many sections have an A?
2, 3.
3 of them. Of course, don't forget to simplify. That probability is also 1 in 2. Okay? Step 3. Multiply them together. And everyone, our chances of winning this game, let's see, 1 times 1 is 1, 2 times 2 is 4. Our chances of winning this game, we have a 1 in 4 chance of winning. All right, before I have you guys try one, any questions? Okay. Here we go. The problem I want you guys to try out is problem number 1. Number 1, go. Can you get one? And I'll take that one from you if you'd like. All right, anyone need more time? All right, 30 seconds. Go ahead and turn to your neighbor and share. Go.
I got 1 in 48.
All right, here we go. So on this problem, right, probability, just looking, probability of spinning a 4 right here. Well, there's 8 sections. A 4 is only on one of the sections. It's 1 out of 8. The probability of the second event happening, I need to be careful, but remember, these are 2 separate spinners. So these are independent events. The second one's not affected by the first. So spinning a C, in this case, right, there were 6. A C is only on one of the sections. It's 1 out of 6. All I do is multiply my fractions, my ratios, and I get a 1 in 48 chance. Okay? I'm not going to play that game. All right? That's not at good odds. All right. Questions on that? All right, here's the next one I wanted to try. Let's go ahead. Let's go down to number 10. Okay, let's go ahead and close read the game. It says there are 10 yellow, 6 green, 9 and 5 red cards in a of cards turned face down. Once a card is selected, it is replaced. Find each probability. All right. So here we go. I'm going to go ahead, and you're going to see me go through the exact same steps. Step 1, probability of a red card. Well, let me see. The total possible outcomes, let me see. How many cards are there? There's 10. 10 plus 6 is 16. 16 plus 9 is 25. 25 plus 5 is a total of 30 cards. Our favorable outcome is a red card. So there were 5 red cards. Now if I reduce that, right? I reduce by 5. It gives me a 1 in 6 chance of winning. So there's step 1. Now step 2, an orange card. Okay? Well, let's see. How many possible outcomes are there?
9. I mean 30.
Yeah, but actually, no, you're all wrong again. Why? It's not replaced. The red card was not put back. There are no longer 30. Okay? There are, remember this? How this was 1/4, but when we didn't replace it, it became 1/3 because there were only 3 cards on there. Well, there are no longer 30 total cards. There are 29. We didn't put 1 back, ladies and gentlemen. 30 minus 1 is 29. 30 cards total. After we took out the 1 red card, there are now 29 cards total. Okay? Then we need to choose an orange card. How many orange cards are there?
9.
Now there's 9 orange cards. All right, now I multiply them. Now, we didn't say this in our notes, but, I mean, when you have big numbers like this, bless you, you definitely cross-reduce. 9 and 29, or I'm sorry, 9 and 6. All right, I can reduce both by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. When I multiply straight across, I get 1 times 3 is 3. 2 times 29, well, 2 times 30 is 60. Yeah, 2 times 29, 2 29s would be 2 less, which would be 58. We have a 3 and 58 chance, 3/58 chance of winning the game. Okay, so now, before I give you one, any questions, especially about the fact that there's 29 cards on possible outcomes? No questions? All right, here's the one I want you guys to try. The one right before it, problem number 9. Try out problem number 9. All right, go. Anyone still need more time? Okay. Give you a few more seconds. Okay, 30 seconds. Go ahead and turn to your neighbor and share. Go. You're pulling one yellow card. No, what? Okay, we'll talk about it, and then if you still have questions. All right, guys, here we go. So, probability of choosing a yellow card, then a green card. Okay, so here we go. So the very first step is find the simple probability of choosing a yellow. Well, I mean, it's the same game, right? There are a total of 30 cards at the start of the game. Okay, and the yellow card, of course, there are 10 of them. So possible outcomes and favorable outcomes. Well, hopefully you guys can reduce each them by 10, right? We have a probability of 1 out of 3. Might as well reduce it right off the bat. Now comes the green card. Because the yellow card was not replaced, there's a total of not 30 but 29 cards. Green, though, there are still the 6 green here. Step 3, multiply them. Well, I'm going to cross-reduce here. 3 and 6, they both can reduce by 3. So this 3 divided by 3 is 1. 6 divided by 3 is 2. So when I multiply straight across, 1 times 2 is 2. 1 times 29 is 29. And we have a probability of 2 out of 29. Did that answer your question? Okay. Guys, other questions? Okay, there's going to be one other type of problem that happens on tonight's homework. So here we go. Let's take a look at problem number 11. Same game. Same game. Here we go. Now, this is, first of all, we have to read into it a little bit. What's the probability of choosing 2 cards that are not orange? Remember, we've talked about that's a complementary event. That not orange means everything else. Okay? So, 2 cards mean we choose a card, just like what we were just doing, right? We choose a card, and then we choose another card. They are still 2 things happening. They're still compound events. So, here we go. What is the chance of us choosing a card, the first choice, that is not orange? So, here we go. They're at the start of the game, again, total of 30 cards. So we've done this a couple days ago, right? With simple events. Our favorable outcome is choosing something that's not orange. So it means all 30 cards except for the 9 orange. You guys were pretty good at this yesterday. How many ways can we win on that one? 21, right? 30 minus the 9. Now, if you don't feel comfortable with that, you could say 10 plus 6 plus 5. But 21 cards that are not orange. 21 out of 30. By the way, I can reduce that by 3. 21 divided by 3 is 7. 30 divided by 3 is 10. Reduce any chance you get. All right? Makes your life a lot easier when you're multiplying. Here we go. Step 2. I go back. I do not replace the card. I go back to choose another. There are a total of, we've been saying it the last couple problems, total of 29 cards. Ladies and gentlemen, how many in that stack are not orange? Ooh, I heard someone say it earlier. 20. Why 20? Because the one we chose, right, was not an orange card. That was one of the winners. So the total goes down, but one of our winners, our winning cards that we can win with, are not in the deck any longer either. Our favorable outcome is not 21. It goes down as well. It's 20. Now I usually don't pause right in the middle of a lesson, but any question, that's very important to know. Any questions about that? How that went down? God bless you. We're okay? So everyone understands, right? We chose a card that wasn't orange. So the total amount of cards are gone down. Total outcomes have gone down, but so has our favorable outcomes because that first one we chose was not orange. And now we're trying to choose another one like that. So there's no longer 21 winners there. There's only 20. All right, here we go. I'm going to go ahead and multiply them. 20 and 10, I can cross-reduce. both of them by 10. This becomes a 1. This becomes a 2. 7 and 29 I can't cross reduce. So when I multiply straight across, 7 times 2 is 14. 1 times 29 is 29. And there is our probability for number 11. And again, guys, on here it doesn't say, at least on these problems, it doesn't say anything about percent or decimal or anything. So that'd be fine for an answer. Any questions on that one before I give you guys one to try? Okay. Here's another one to try. Problem number 8. Problem number 8. Try that one out. Let's go. Bless you. All right, guys. Anyone still need more time? Okay. All right. Guys, those are all the different types. So at this point, while you're some of you that are finished, while you're waiting for other people, right? Go ahead and get going on some of the rest of your homework there, and we'll I'll go ahead and talk about it in just a bit. The rest of you guys finish that one, and we'll share. Okay, 30 seconds. Turn to your neighbor and share. Go. All right, guys. Those of you that are still talking, I appreciate you guys trying to help each other out. Let's wait, and if you guys still have questions, make sure you ask. All right, number 8 says, what's the probability of choosing 2 green cards? So here we go. The very first one, right, is always going to be the easiest because there's a total, like the rest of the, these problems in this game, there's a total. We start with a total of 30 cards. Okay, and so the very first event, right, 2 green cards means a green card and then a green card again. So the first event is choosing a green card out of 30. Well, let's see. There's 6 green. We can actually reduce top and bottom by 6 and get 1/5. Now the second event, right, we know it's not replaced, so we know there's no longer 30 cards at the start of this next drawing. There's only 29. Favorable outcomes. We've already chosen a green card. That's the one we kept out of the pile. So there's no longer 6 green cards. There are now 5. So when we multiply we not only can cross reduce, right? We can cross cancel. 5 and 5, they both become 1s, and we end up with a 1 in 29 chance. Okay, questions on that one? We're okay? Guys, two things. First of all, I want you to make sure, remember, going back to our steps. Step 1, remember, always reduce. You can try to reduce step after step 2 as well, but it can happen sometimes. Step 1, reduce. It makes your multiplication easier. But here's the main point. Step 2, this is a very important star. In this particular case, depending on the game, you have to be very, very careful. You can go fast with step 1, and maybe even to a certain extent step 3 if it's a pretty easy multiplication problem. But step 2, take your time. That's where you want to slow down and really give it some thought, because that's where most people will miss the problem. So be very careful when it comes to step 2. All right. Make sure, especially independent or dependent, what's changing? Is just the possible outcomes, or is the favorable outcomes changing as well? We saw them both ways. I do want you guys to really quickly, number 15. Okay, there's some information here. It's about someone going to rent a car. Okay, you have all these different kinds of cars down here. All right, and then you have a little story over here. I want to talk about two things. Okay. There's two different elements here, or two different, events. One is the type of car, and then one is the gender, meaning a man or a woman. Okay? So, I want to first of all say, those are your two different elements, or your two different events. Okay? Is the car type and the gender. Okay? Now, here's the other thing. I would recommend, of course, change all percents to fractions. Okay, then it becomes like all these other problems here. Okay, convert them percents to a fraction. Remember, if I took 25% and converted it to a fraction, I would say 25 over 100. And then if you can, reduce. Okay, some of them you won't be able to reduce, others you may. I would do that and then go about doing all the problems. All right. Okay, guys, independent versus dependent events.